So sometimes when we're doing dyno pulls and stuff like that on a dynamometer, we often see that torque and power seem to magically cross at 5252 RPMs. And that might seem like a magic number, so I'm gonna be here trying to hopefully make sense of that and show why it's not exactly magical. So I guess first things first, we'll probably start with the definition of 1 horsepower, right? So 1 horsepower is equal to 33,000 pound force times feet, or pound force feet per minute, right? So basically, I think what I'm gonna do first is I think I want to create an equation for this. Maybe relate power to force and displacement, or in feet and time in minutes. So I think I'm gonna say that power in horsepower is equal to force in pounds force times displacement, I'm gonna call it x, in feet over time, right? Time in minutes, divided by 33,000, right? Now I'm gonna test run this equation, make sure that it makes sense, make sure that it works. So I'm gonna test run this with the values we have right here. So 1 horsepower is defined as applying 33,000 pounds force over 1 foot in 1 minute, okay? So if my F is 33,000 pounds force, so we have, and our displacement is 1 foot, and our time is 1 minute. So my power is going to be 33,000 times 1. I should probably write this actually. We're going to get power is going to be equal to 33,000 times 1 foot, 33,000 pounds force times 1 foot over 1 minute over 33,000. And what do you know? That's all equal to 1 horsepower. So our equation checks out. That's pretty cool. But here's one thing I noticed. I think I want to make some changes to my equation real quick. I have here displacement over time. We know that displacement over time is equal to velocity, right? So I think I could write my equation like this. I think I write like a little better. I could say that maybe P is equal to force in pounds force still, velocity in feet per minute over 33,000, right? So, alright, I have a nice equation. But here's the thing. On dynamometers and stuff, we're usually dealing with rotation because it measures the rotation of the wheels and stuff like that. This force and this velocity, this is a linear velocity. So I think I'm going to need to find a rotational analog for our power equation. That's pretty easy to do because when we're rotating stuff, force, the rotational analog of force is torque. So this is tau for torque, I guess. So the rotational analog for force is torque, and torque is going to be measured in pound force feet, right? And our velocity, here's the thing, our linear velocity gets translated into rotational velocity, omega. This is omega. But here's the thing, the units of omega are actually in radians per minute. Because in physics, like if we're, well, let me write my full equations first. So our omega is in radians per minute, and we're dividing by 33,000. So here's the thing, in physics, radians kind of doesn't actually count as a unit. So when I say like things like, when I'm doing unit analysis and stuff like that, I'm doing arithmetic with units, radians per minute, I'm going to do this off to the side real quick, radians per minute is kind of just really equal to 1 over minutes, if that makes any sense. So when I do the multiplication stuff, I'm getting pounds force feet, because that's what torque is. That's the units of torque. People will say pound feet, doesn't matter really. So we have pound feet times radians per minute, which is actually really equal to 1 over minute. So our final unit, I guess, is just pound force feet per minute, which is what we have here, which correlates with a horsepower. So that's why omega needs to be in radians per minute. So let's see here. So we have our equation for power in terms of rotational stuff, things that actually show up on a dyno chart, like torque and angular velocity. So I think what I'm going to do is I want to find the magic angular velocity, not RPM yet. I want to find the magic angular velocity for which power is equal to torque. Alright, so if I say that power is equal to torque, right? Power is equal to torque. I think this is the correct way to draw a tau, but whatever. Say power is equal to torque. I'm going to replace any one of these with each other. I'm going to replace power with a tau. So I'll get tau is equal to tau omega, this looks like a J, this is terrible, over 33,000, right? And these two cancel, and we get that, I'll do right here, 1, so 1 is equal to omega over 33,000, 33k. We get that omega is equal to, well, 33k. That doesn't look like 5252. That's because this is in radians per minute. Radians per minute. We need to convert this, radians per minute, into something that we actually use, because no one actually uses radians per minute. We all use RPM when we're talking about dynos and stuff. So we're going to do a little dimension analysis. Hopefully you can see this. I think you can see this. So let's see here. Radians per minute. We know that there's 2 pi radians in one full circle. So 2 pi radians in one revolution. So to convert to revs per minute, we're going to just multiply by 1 rev over 2 pi radians. And that should get us our magic RPM, because when we do the math, we're gonna get our answer in RPM. So I'm gonna whip out my calculator. So basically what we need to do is to convert this to RPMs, we need to take our 33,000 divided by 2 pi. So hopefully you can see my calculator. I'll move this off to the side a little bit. So you should see my calculator. You should be able to see the magic I'm about to do. So I'm gonna take my 33,000. I think you should be able to see this. 33,000 divided by 2 times pi. And let's see what that comes out to. Look at that, 5252 and a little change. So, guys, the conspiracy is true. 5252 is the magic RPM, for which power is equal to torque on a dyno chart. So, guys, it's been proven. And stay tuned for more stuff like this, more mind-blowing stuff like this. Get rid of that 0. But yeah, follow for more stuff like this.